All right, stay connected, everyone.
All right, the recording has started. Yes.
Okay, then an official welcome to everyone to this session for Machine Learning for Software Engineering 5. Most of the speakers are here. Thank you for coming. We have some exciting papers. I watched the full papers a couple hours ago. Very cool stuff. We're going to have around 5 minutes for each of the speakers here for a little pitch of their work. Tonight, I'm pulling double duty. I'm the session chair, but I'm also a speaker of the, in this case, first paper. So yeah, let's all have our pitch one after the other. And then if you do have questions in the audience or to each other, the speakers, either note them down somewhere or put them in the chat, and we'll start the discussion after the talks. Okay, in that case, let me get started. Okay, someone dropped. Was it Simon? All right.
All right, I'm back.
There you go. Okay, you should be able to see my PowerPoint.
All right, yes.
Perfect. All right. So let me try to give my pitch on work that I've done during a sabbatical with Meta, back then Facebook, called Counterfactual Explanations for Models of Code. Okay, why is it progressing on its own code? And this is joint work.
We see
Sorry?
the whole window. We don't see slides.
Oh, you don't see slides? Thank you. Then let me just share it differently. How about now?
It looks great.
Okay, thanks. So yeah, this is joint work between myself, Jürgen Sito, Ishil Dilik, Vijay Murali, and Satish Chandra. Why is this happening? But the topic here is machine learning models of code.
Work that uses machine learning for
Oh, all right. I know what's happening. Sorry. There you go. Okay. So the topic that is at the center here are machine learning models of code. And if you look in the literature, there are a bunch of models out there that, through some trained model, look at properties of source code. One of them, for instance, is a paper from NeurIPS 19 that looks at C and C++ source code and can detect vulnerabilities, privacy and security vulnerabilities in that code. Another one that officially called semantic code labeling, but more colloquially known as method name prediction, appeared in POPL 19. And at Meta, we have our own machine learning models of code. In the paper, we go through 3 of them. There are a couple more that we use. The one I'm going through here as an example is performance regression detection. So let's imagine you're trying to commit the code on the right-hand side here, and the machine learning model that is in charge of telling you whether this code may introduce a performance regression says alert, red alert, something's going on here. And you as a developer, without any context, might ask yourself, well, why does the model think this code will lead to a performance regression? And if it's only 10 lines of code, you may have a certain hypothesis going on. But imagine this is hundreds of lines of code that you're trying to commit, then it might become a bit harder to understand what's going on here. So here, cue counterfactual explanations. To introduce the former term, counterfactuals is a term from literature of causality, which means an alternate world where prior circumstances of that world have changed, and then we assess the consequences of these changes. So if you look back to the example that we saw before, imagine you see this here in the code example, and you could verbalize it in the following way. You could say, if you had called gen simple instead of gen handle, your code would not be classified as causing a performance regression. And that is what counterfactual explanations can do for us. What they do is they demonstrate how the model's prediction would have changed had the program been modified in a certain way. And it does that by posing a bunch of what-if questions to the model, and then determines which of one of those what-if questions actually turns the prediction beyond the decision boundary. So on a high level, we can look at this as an optimization problem. So which combination of input tokens in my code do I have to change in a certain way to flip the model? And the change between the original world input and the counterfactual input is what constitutes that explanation. So I go into more details in the longer presentation in the paper. I'm going to skip the details on the algorithm and the optimization for now. And I'm going to go through a concrete example to show you how that would actually work. So let's imagine you have a tokenized representation of your program that will look something like this. The first thing that the algorithm will do is it will identify one token explanations and then prepare expansion candidates for explanations that are larger. So a one token explanation could look like this. Imagine if you were to change one token, namely set exception stack, to instead called set message, that would constitute a change in the prediction. Meaning, and if we verbalize this again, it would say, if you had called this other method instead of set exception stack, we wouldn't have thought this will be a performance regression. And one thing that we go through in more detail in the paper is that we're leveraging natural perturbations. We're not doing something that more feature-based attribution methods do by, for instance, removing certain features from the input, because we want to keep the input in distribution. Now, what this also does in the first pass is, now that we've identified one token explanations, I don't know what is happening. We're sorting all the other tokens by the score differential. So we're going through all the other tokens and looking at, if we were to perturb these tokens in a certain way, how would the score change? And this gives us a proxy of how far we are at the decision boundary. So in all the other iterations of our optimization loop, we expand these likely candidates sorted by the differential by one more token. Let's see, in the first case here, the most promising token would be set exception summary. However, in the concrete loop, executing this, we see that no expansion with this token actually leads to a change in prediction. So we have no explanation here. However, if we change the response body with action.type, and we also change the app ID to ID, we then get an explanation that has n tokens. In this case, the n is equals to 2. And then we increase the iteration size more and more to get larger explanations if we want to get larger explanations. So the iteration size here is a hyperparameter that we can set. We went through a couple of experiments with software engineers at Meta to answer the following questions. Number one, we wanted to know how useful are these explanations when engineers are presented with them. And what we saw here is on the right-hand side of this table through our user study is that in about 83% of cases, people found these explanations useful. The second question that we ask is, do these explanations help the engineers to discern between true positive and false positive predictions? By that, we're acknowledging that these predictions are imperfect. There's uncertainty involved. The accuracy is not always up to par. However, in order to distill trust in the prediction, the explanation can help the developer in discerning between true and false positives. And one interesting aspect that I want to highlight here is that in the true positive case, the explanation helped the engineers reinforce their mental model. And in the false positive case, the explanation pointed to a very unreasonable part of the the source code. And that gave the developer confidence that the model picked up on the wrong signal. The last experiment that we did is we compared the explanations that we produced with human rationale that we gathered through a qualitative study. And we saw that our approach produce more human-like attributions more consistently than a baseline approach. To finalize here, what I wanted to show you today is if you have a certain black box machine learning model that tells you about a certain quality characteristic of your code, as a developer, you may ask yourself why, especially if the code that you're looking at is pretty large. And the way we deal with this is we generate counterfactual explanations with a greedy guess and check approach, where we leverage masked language model perturbations to keep the perturbations and the input in distribution. And that constitutes this contrastive nature of explanations that shows us how can the code look differently in order for the model not to think the way it initially thought so. The code that produces all these counterfactuals will be open source very soon. I have to just clean it up a little bit. If you do have any questions, please reach out on Twitter or by email, and I'd be happy to talk about it later. Okay. All right. So next up, is our first speaker already here? Amin, in that case? I don't think so. So in that case, let's move on with Jeremy, actually. Take it away.
All right, 1 second here. And here we go. All right. Hi, everybody. My name is Jeremy Lecomis. I'm a PhD student from CMU, and I'm going to present varclear, which is our novel framework for representing the semantics of variable names using contrastive learning. So recently, I've been working on techniques for replacing variable names with more meaningful ones in situations where they cannot be recovered. So for example, decompilation. So this is an example of output of a decompiler. And this is the original code that was written by the developer. So far, our metric has been, does the suggested variable name exactly match what the developer wrote? But this has some shortcomings. So for example, current would not be considered a reasonable replacement for cur here, even though they clearly have the same natural language semantics. So this current and cur example seems relatively simple to fix. It's just an abbreviation. But considering only abbreviations misses a lot of other cases. For example, length and size would not be considered semantically similar, even though they are. And other metrics such as edit distance don't quite work. For example, min and minimum, they have a large edit distance, but they are very similar. So another option would be to use natural language processing tools like word2vec that assign words to points in an embedding space where related words are very close together. So this seems like a good idea, but it has different shortcomings. So as you can see in this word2vec model, the closest point to the word minimum is maximum, which happens to have the exact opposite meaning. So instead of closely related names, what we'd like to do is generate similar names that can be used as direct replacements. So for example, min length and minimum length are related but similar, while min length and max length are related, but they're dissimilar. You can't use one to replace the other. So last year at ICSE, there was a paper on ID-Bench. What it did was it evaluated how well state-of-the-art machine learning-based methods align with human developers' judgments of variable meanings. One of the benchmarks asked developers to rate how related two variable names are, and they found that approaches like word2vec and fasttext are actually quite effective at representing relatedness. I apologize for the noise from my cat in the background. However, they also found that similarity scores generated for these pairs of variables disagreed with human scores completely. So instead, our approach uses what's called contrastive learning, which is a technique that was originally developed for computer vision. For example, we would like to learn that the minimum score of an accepted ICSE paper is 3 is close to 3 is the minimum score of an accepted ICSE paper, but far from the maximum score of an accepted ICSE paper is 5. So methods like word2vec that only consider context are just unable to learn this distinction. The way this works is by being trained with labeled pairs of data. So contrastive learning minimizes the distance between data that is labeled as positive pairs, and at the same time, it maximizes the distance to every other point in the embedding space. So this means that we just need labeled pairs of similar variable names to train a model. So for our training data, we automatically generated a data set that we call GitHub renames. This was created by scraping GitHub for commits that only rename variable names without editing any other code. So on the screen is an example from our data set. And if you'll note, numTrees is changed to number of trees, and min data points in leaves is changed to minimum example count per leaf. This full data set is available on our GitHub repository. So Varclear improves on the state of the art. For relatedness, we improved the Spearman's rank correlation score for agreements with humans from 0.73 to 0.8. But more interestingly, we also improved similarity scores from 0.35 to 0.53. And you could check the paper for more results and details. And I also just want to stress that Varclear isn't only useful for decompilation. Scoring the similarity of variable names comes up all the time in other problems, including suggesting better names during coding, remapping APIs from one language to another, and detecting subtle bugs from typos. So just concluding, I'm Jeremy Lecomis. I'm part of both Strudel and Squares Lab at CMU. These two QR codes on the screen link to our paper and the GitHub repo if you want to try it out. The repository contains all the code we used, the GitHub renames dataset, and pre-trained models that could be used without a GPU. Thanks for listening.
Thank you, Jeremy. All right, then Boyan, do you want to go next?
Sure. Let me start. You can see my screen, right?
Yep.
Okay.
Yep.
Hello, everyone. My name is Boyan Chen. I'm currently a senior researcher from Huawei Canada, and this is a joint work with my colleagues and Professor Jeremy Jiang, New York University. The talk is about towards training reproducible deep learning models. A paper published in Science in 2018 suggests that the domain of AI faces a reproducibility crisis. And they surveyed about 400 papers and find out like many research papers do not provide sufficient information for replicate the results. And in this paper, we consider the term reproducible as if under the same training setup, the result trained model yields the same results under the same evaluation criteria. And this definition is from a checklist from NeuralNIPS 2019. It is very challenging to reach reproducibility because the model, data, environment, and the code need to be carefully documented and managed. Even with all the information provided, we still see that there's turbulence in the ending performance of the model. So in general, there are three challenges of training reproducible deep learning models. Is the software randomness cause the results non-stable? As you can see in the figure that if you pick different random seeds, sometimes it will give you statistic different results. And there's also the rounding errors, or like one example of hardware non-determinism when you're training models using GPU is the rounding errors, where like the sequences of the adding of floating points could actually affect the results. The third challenge is the lack of systematic guideline to help people to build the reproducible training process. So there are a couple of ways that training reproducible models nowadays. Like one of the most obvious ways dealing with software randomness is setting random seeds. But in a lot of the cases, people feel reluctant to set the seeds as it is intrusive, difficult to manage. and also it limits the exploration scope. For the hardware randomness, non-determinisms, there's APIs, environmental variables you can set, but there's lack of systematic evaluation. And also there are like model cards, data sheet, but there's no automatic process to validate. So to tackle that problem, we propose our approach, and the general overview look like this. So in order to verify if the model is reproducible, we conducted a couple times of training. We first conduct the initial training and then verify the results. If it's reproducible, then we think the process is finished. If it's not, then we conduct a profiling and diagnosing process, updating our strategies, and apply the record and replay mechanism, where I will introduce soon. During the procedure, there's evaluation metrics, process metrics, and models, and intermediate files such as random profile were generated. So to control the software randomness, we propose this mechanism called record and replay. We first use strace to trace the system calls that may introduce the randomness. And as the left side of the screen, you will see that under the Linux systems, the open device of dev urandom and the system call get random will introduce randomness in the training process. And on the right side is our mechanism is called an API hook. Basically, we're just using the LD preload environment variable to set up a wrapper function such as this get random. And in the first training time, you just train as normal, and the get random will act as a wrapper to call the real get random to get the random data, put in the storage. And in the replay process, you still call it get random, but this time this random will not call the actual get random. It will go through the storage and get the data for you, which is the same with the record process. And then this replay process will fed into the replay training process. And then they will basically share the same random state. For controlling the hardware non-determinism, we apply a profile and patch. We first apply a profiling tool. In here, we use cProfile, but in essence, you could use any profiling tools you like. The key is to get the functions that was actually called in the like the operators. And we use the open source non-determinism patch from provided by NVIDIA. They have this fine list of APIs that they think they would be possible to introduce non-determinism, and we apply the patch accordingly. So we set up our case study with 6 popular CV models and 1 commercial model. We run 16 times, which are divided to 8 pairs, and compare the results. The detailed information were in the papers. I'm not going to introduce it here. Basically, as the evaluation results show that not only we reach the full same results of all the models were trained, but we also can have the exact same process metrics, which is like you see the losses, the accuracies during each epoch. Basically, all the model generated will give you the same results. And the overhead for the storage is like the random profile generated is a few 13 kilobytes to 38 kilobytes, and the time overhead were there were certain time overhead due to the patching of the GPU operations, and the longest overhead, for example, for wide ResNet is about almost a double, but for the others are So as a summary, the domain of AI faces reproducibility crisis, and people are trying to reproduce the results as shown in research papers, industrial models, and so on. And we propose a full end-to-end process to train the reproducible deep learning models, and that involves a record and replay method for controlling the randomness, profile and patch for controlling the hardware non-determinism. We evaluate our method on 6 popular CV models, 1 commercial model. And the evaluation results shows that both the process metrics and the evaluation metrics can be fully reproduced. To know more, you're welcome to contact me and ask any questions. All right, thank you.
All right, thank you, Boyan. Next up, we have Nadia.
Okay, let me share it. Can you see it?
Yep.
Yes, perfect.
Okay, so hello everyone. I'm Nadia Nahar, a software engineering PhD student in Carnegie Mellon University, and I'm going to present our paper titled as Collaboration Challenges in Building Machine Learning-Enabled Systems. So I hope you have seen the longer version of the presentation. If not, I hope I can make you interested to look into that. So I always like to start with this example. When thinking about a machine learning system, we often think of a notebook where we can write some code to train a model and have an output of a prediction in some form. So for example, this is a face detection model that detects a human face in images. So now this face detection model is not an application or product in itself, but if we want it to be used by end users, it may be embedded inside a photo app as a component, which will look something like this. Now, this photo app does not only contain a machine learning model, it has many more components along with this model. The machine learning face detection model is only one component of this entire system. So for building this kind of system, we need many different roles to work together. So there might be a group of data scientists who we can call as a model team, who will be in charge of the machine learning model. There might be software engineers in charge of the other engineering parts, who we can call as a product team. There can be a data team for managing data and many other different roles like managers, domain experts, and so on. So now talking about such projects, we find many articles that talk about a large number of data science projects never even make it to production. And among the issues, we find the problem of lack of collaboration in different forms. That leads to a lot of problem. So we felt it was important to look deeper into the boundary between the disciplines because that's where a lot of problems seem to be. So this led to a research question to find the collaboration points and challenges between different stakeholders, especially the software engineers and data scientists. So it was a qualitative study where we conducted 45 interviews in 28 organizations. It was a 4-step process to come up with a theory. I'm not going deep into the methodology due to the time constraints. So this is what we came up with. There are 3 major collaboration points where the interviews were facing most of the challenges. So here you can see the topics, the subcategories, and some icons beside the topics. So these icons are basically the themes of different collaboration challenges that has been happening. You can see in the bottom of slides the name of these themes, and you can also find it in our paper title. So now, not all the companies face all of these challenges that we have found based on the different team structure and working style. Different teams face different challenges. So I'll show you one example of a challenge from the requirements collaboration point. So in this collaboration point, the primary collaborators are the product team and the model team, and the client and the management are also involved in shaping these requirements. So suppose this organization named Organization A has a banking software, and now they want to detect fraud in that existing software. So the requirements for this company flows in a way like this, that the manager and the product team first comes up with the product requirements, and then the product team talks to the model team, transferring the product requirements to the model requirements, and the process goes on. So we categorize this type of organization as organization of product first trajectory. So because the product was developed first, and then they feel the need of a model, which came later in the process. The problems that this kind of organization face is that when the product team comes with the requirements with the manager, they do not include the model team. As a result, they come up with requirements that might not be realistic. For example, the product team might decide to detect all the frauds in the product, but we know that machine learning is not capable of providing 100% accuracy. So now when the product team talks to the model team says that it is not possible for them to build such a model. So it creates conflict between the product team and the model team. Also, as it is very late in the process, the success of the product gets put at stake. So as you can see, we found 2 themes around the collaboration point at this point of the organization. One is problem of communication because of not including the model team during the requirement process. And the second one is of documentation because we have seen that often the product requirements are translated into model requirements verbally without any written document. So this elevates the conflict of the 2 teams more. So as recommendations for mitigating the first challenge, we recommend to include data scientists early during the requirements phase, not afterwards. And for the second challenge, we recommend to maintain formal documentation for both product and model. So as you can see, I only showed one challenge in one problematic topic. There are many more that people face in all these collaboration points. And as you can see in the themes, a lot of challenges can be mitigated with better communication and documentation and a little emphasis on AI literacy education. And we also need to appreciate the engineering effort more to make this kind of product successful. And also there is a scope of research in defining good process for this kind of machine learning system. So I hope you read the paper and get to know all about our findings. So due to time constraints, I'm not going to go deep into any challenges right now, but I'll be more happy to discuss about this with you afterwards. So in summary, collaboration problems can lead to failing of software machine learning products, and thus it is an important topic which we need to put more emphasis on. So from talking to 45 practitioners from the industry, we figured out the 3 main collaboration points that need special attention, and we also try to provide some recommendation based on the industry best practices and existing tools and techniques of software engineering. So thank you. That's all from my part.
All right, great. Thank you. Okay, then our last speaker, Hongjin.
Okay, so my name is Hongjin, and now I'm going to talk about work on detecting false alarms from static analysis tools. So the context of this work are the warnings produced by static analyzers, such as Findbugs. So the warnings produced from these tools represent real bugs. So in other words, a warning could be an actionable warning or could be a false alarm. So one line of research aims to solve the problem of the numerous false alarms by introducing a classifier in between the warnings and the developers. So if the classifier predicts that a warning is a false alarm, then it is not presented to the developer. So this would save the developer a lot of time. So in the literature, many different features have been proposed, but one prior work has identified the most important features from the literature. So these are called the golden features, and subsequently, another work found that the use of the golden features in machine learning achieves very strong performance of up to 99.5% AUC. So to construct the data set for these experiments, we will need a training data set and a testing data set. So one way of doing this is to identify a revision of the project as a training revision. And then this is where the data will be collected and to train a classifier. And the classifier can then be deployed at the usage time. So we would collect the warnings for the training revision and compute the features as well as the labels for each warning. And then we do the same at the usage time, collect the warnings and compute the features to construct the testing data set. So in the prior work, in order to determine the labels of each warning, a heuristic was proposed to compute the labels. So this heuristic involves the comparison of warnings at a given revision and the warnings at a reference revision, which is set chronologically in the future of both the testing and the training revision. So an open warning refers to a warning that was present at a given revision and is still present at the reference revision. And prior work assumes that open warnings are false alarms. And a closed warning refers to a warning that was present at a given revision, but is no longer present at the reference revision, even though the source file is still present. And prior work assumes that closed warnings are actionable warnings. So we analyze the golden features, and one interesting class of features are called we call them the warning context features. So these features are always the most important features that contribute to a prediction. So these features essentially capture a proportion of actionable warnings in a given context, say a method or a file. The intuition here is that if developers have historically fixed warnings within a method, then perhaps they are more likely to fix warnings that appear in a method in the future. Right, but we find out there was an issue of data leakage when computing the proportion of actionable warnings. So to compute these features, we would collect the warnings for a context, say a method, and then we would check the status of these warnings at the reference revision by checking if the warnings are still present at the reference revision. So this introduces a problem because this was the same procedure that was used to compute the ground truth label of the warning, and essentially this leaks the ground truth labels into the features. And furthermore, this is also unrealistic because computing the warning context features means that we already know the status of the warnings in the future, and this assumption would likely not be true in practice. So we also found other issues of data duplication due to the way the warnings are collected for the training and testing data set. And we find that the strong experimental results observed in prior work stem from these subtle issues. So these issues are very hard to detect, but we see that they had a significant impact on the performance. So initially, we start from an F1 of 0.88, and after we address the issues, including the re-implementation of the features with data leakage, the F1 drops to 0.38. So the next thing we investigate is the heuristic, and we wish to check if human orators agree with the labels produced by the heuristic, which assumes that close warnings are actionable warnings. So we essentially perform data annotation with two authors, and then we find that many close warnings were not actionable. So while many warnings were close, by close again, we mean that they were present at the given revision, but were no longer present at the reference revision. But we find that many warnings were close for reasons that were unrelated to the warning, and as such, we cannot say if the warning was actionable or not. Right, essentially our work was a triumph of open science. The previous authors did excellent work, and we built on top of their work, and they very generously made the data and scripts available so we could build on them. So we find that the Godin features suffered from subtle issues of data leakage and data duplication. However, we note that the Godin features are still predictive with an AUC greater of 0.5. In our work, we only use very simple classifiers such as a SVM and k-nearest neighbors classifier. So our work does not show that this task is impossible or impractical, and instead it only motivates the need for more work and analysis. So we also see that the use of the heuristics allowed us to generate a large data set, but the labels did not necessarily agree with human orators. So our work has the following implications for the future. So essentially, we need more manually labeled data, or we need methods that can address the lack of labeled data because labeling could be very expensive. So I'll be happy to discuss all these points in greater detail. But that's all for this 5 minutes presentation. Thank you for your time.
Fantastic, thank you. Yeah, thank you everyone for your pitches. For the audience, if you haven't done so, go look at the full presentations, go look at the papers. But yeah, now the floor is open for questions, discussions. If you do have a question, feel free to unmute yourself. However, beware that this session is recorded, so your voice will be in the recording. So if you don't want that, just drop us a message in the chat, and I think we'll be all happy to start a discussion, answer the question. Otherwise, also the speakers in the session, if anything came up during these pitches that you want to start a discussion on, please feel free to just unmute yourself and get started.
I mostly want to. This isn't really a question as much; it's just an observation. I just want to say that specifically with Hongjin, it's really nice to see a reproduction study in software engineering. This is like a thing that we never see, and I'm really glad that this is happening now.
Yeah, I agree with that. I think the software engineering community would benefit a lot more from replication studies and stuff like that.
Yeah. This is why we try to make our code available as much as possible,
Yes.
and our data. I actually get a lot of people trying to use our code and asking for support and stuff, and it's really nice to be able to provide some support.
Right. Yeah. Of course.
Yeah, no, absolutely. On both ends, so just if at all possible, make your code and data available. Artifact evaluation tracks, also a pretty cool thing. I hope you all participated in this year's ICSE. No, not this time. No, we're working on improving that too. Like I think that there's good work on a meta front to make these tracks also less overhead, but I do see the value of any sort of open sourcing. So open science in general, be it through an artifact evaluation track or not, is the very best thing you can do. And it enables the important work that Hongjin has done here. That's very cool.
Thanks.
Yeah, maybe I can just then follow up with your paper. I mean, you've identified super interesting things that are happening. I think not only for this particular sort of paper, I think things like data leakage and in general, just using random cross-validation when we have data sets that are very sequential is not the right thing to do. Into the room, basically, and also to the people in the audience, if you have an opinion on this, what do you think as a community we can do to improve this situation? Like, what can we do that in the future people that do work on these things employ the right methods?
I guess I could start. So I thought this year the ICSE review had a very transparent set of processes and standards. So that was nice. So I'm also aware of some work on standards for empirical studies. So it seems like our community is heading in the right direction, where we establish all these standards that are they're made known to everyone. So we would have no choice but to look at the standards when we perform our studies. So that's a good step, I think.
You're referring to like the empirical standards that I think Paul Ralph started out, right? Yeah, right.
Yeah, that's
No,
right.
I think that those are fantastic. I do feel that there may be, at this point at least, not as well populated for ML for SE work so far. There's a lot of stuff for qualitative studies, case studies, action research. I think at least the last time I looked into it, there wasn't that much about machine learning research within software engineering. So maybe that's something that we as a sub community that works on these kinds of things can come together and figure out some content that we can add as a contribution there for sure.
Yep.
Any other thoughts on this matter? Like one note that I had is, should it be more standard to do more in-depth qualitative analysis of what you're actually testing in your validation set?
We've had entire fields just die when aspect-oriented programming, for example. There were conferences on it, and this is very flippant of me, but someday one person said, "Hang on, what are we actually studying?" and did and asked some developers, "Is this useful at all?" And other than things like debugging, it ended up not actually being terribly useful. So yeah, I do think you need to think about who your target audience is.
No, it's such a very classical ML thing to do. You have a certain set of benchmarks, and you do everything correctly from a methodology perspective, but then eventually you're missing what's actually happening when you're performing this validation step, right? So I do think at least just poking at what's happening in validation could make some sense.
So to be clear, I am like a fan of science for the sake of science, but if you're going to be, purporting to be helping software engineers, you kind of have to actually measure if you're doing that thing that you're saying you're doing.
Yeah.
Yeah, I guess it's just the nature of the field, because it's they're practitioners of the field, and they're more important than the researchers in a sense. So we can't avoid talking to them and checking if our research makes sense to them.
Yeah, I agree. Like when I was doing this interview study, I had so many ideas of what might be happening in the industry, because in the research we had a lot of discussion on fairness and other explanatory attributes that we think of machine learning system. But when I talked to the people in industry, there was a complete different perspective they were looking at the machine learning system. So yeah, it makes sense to sometimes let's go back and check what's actually happening in industry, and then again come back and do something in research.
Yeah, maybe Nadia, if I may, I want to follow up from my notes here. In your full presentation, you went a bit deeper into the point of lack of ML literacy, which I found super interesting between these different teams, right? And I was wondering, in your interviews that you did and in the analysis, what were the different ways that people dealt with this uncertainty of the model, the lack of accuracy? And one thing that maybe it's in the paper that I definitely have to look into from the work that we have done here at Meta is explanations are the one thing, right? Like, how do you instill trust in a certain model that is uncertain? Well, explanation could be one way to do this, but what other things have you seen in your research?
They're talking about explanations. So I try to pitch a lot with the people, trying to understand if they have any other quality concerns other than accuracy. Like, I was trying to understand if you have concerns on fairness, explainability, security, privacy, this kind of things. But it seems like it's a concern in the big techs right now. So the big techs have good framework and structures already working on these machine learning systems, and now they're thinking about this fairness and explainability to incorporate in those. But the mid-sized companies or the startups, they're not there yet. So they're mostly like trying to build something and make a like production system that works. And so they're not like most of the interviewees I talked to, they are not thinking about fairness or explainability at all. So I had to like ask more like multiple time and try to like make them understand what I mean by asking these kind of questions. And I saw, okay, there's nothing yet there. And about AI literacy thing, it was a big problem. Or like not only in the startups and the mid companies, also in big techs, because all the practitioners from these different type of companies had the same complaint that when they work with different team members who are maybe software engineers or a project manager or the client themselves or someone from the operations, they find it hard to make them understand that what this machine learning system demands for. So when the project manager is planning for the entire project, they are not taking in consideration that machine learning is exploration phase and they might take more time than I'm anticipating. So there is a lot of conflicts based because of that. And many companies have been tackling this with like different approaches. Like I saw some companies were having some training sessions upfront. So before going to diving to the machine learning model, they would have some training session with the manager, client, and everyone, and let them know that, okay, machine learning is like that, it doesn't work in this way. So you have to provide me this data or this kind of time if you want me to build a good model. So these training sessions were working for some companies. But yeah, it's mostly like, if you're aware that there's an issue like that, so you might be able to fix that. But when there is no awareness, like when the project managers are not understanding, okay, this is a different type of problem I'm dealing with, then the issues get raised a lot. So yeah, a lot of data scientists had a lot of frustrations because of that part.
No, very interesting study. I'll definitely have to look deeper in the paper.
A follow-up question for Nadia. So earlier in the presentation, you mentioned that one way to bridge the communication was to have formal requirements for both the product people and the data scientists. So what would these formal requirements look like? Because when I think of formal requirements, I think of formal specifications, and we all know that developers are very afraid of formal specifications.
Yeah, I know. Like, so documentation is always like intimidating. I understand that, but the main reason we recommended this was because there's a lot of inconsistency between different people. They had like many different assumptions from the same system. So if you talk a data scientist of a team, he have completely different assumptions, and the software engineer have completely different assumptions. So we're like, when they're talking verbally, many of the assumptions doesn't transfer well. So they're not understanding each other enough, or they don't have the same like verbal communication with same terminologies, conflicts of different things. So when they're communicating, there was a lot of issues that were just mistook for something else. For example, when the data scientist was talking about performance, the software engineer would have think about the time when the data scientist is mentioning about the accuracy. So there's a lot of miscommunications like that. So for mitigating that was a way, like we're recommending this, like maybe it will not be very formal, maybe a semi-formal thing, but at least we should have some documentation so that if there is some issue, some conflicts on some part, we can refer back to the documentation. Okay, we had these assumptions, and this is how we move forward with the system. So yeah, just verbal communication just doesn't really work. So formal document, I don't mean like formal method or something, but yeah, maybe some form of documentation between the different teams so that they agree on something. So yeah, that kind of documentation.
Right, I understand. So like proper definitions where that's listed out explicitly. I see.
Exactly. Yeah.
I mean, I guess room for research. Like, what does a semi-formal language look like to bridge the gap between those two? So there you go. You opened some cool new research.
Yeah, like when I was studying this, I read something about a boundary object where like you share some documents with different types of people and they will find the places where they're interested in. So you're like describing the same system to different people and they're trying to grab different parts of it, trying to understand from their perspectives of that. So I think this something like this in machine learning and software engineering system can work. So I didn't go really deep into that part, but I think, yeah, that's some place we can start from, the boundary object kind of stuff.
Interesting.
I want to direct me one question that I have here in my notes to Boyan. I think that was a really cool way of just interjecting it on like a systems level to eradicate some of the randomness that happens, right? The overhead did intimidate me a little bit though, like, and I totally understand, like, if you have to interrupt the system on this level, that this overhead will occur. What I wanted to ask you is, especially when you think of, iterating over certain model properties or using things like AutoML, where you're or any sort of search for an architecture, do you think that your approach would also make sense, or would you use it at a later stage? Or to put it differently, what are situations where you say you shouldn't use this approach yet?
Yeah. First, thanks. It's a great question. And for the first question, I think I would like to clarify about the overhead. So there are two approaches applied in basically the software side and the hardware side, right? So for the software randomness side, actually, it does not incur overhead that much. So it basically is negligible. The main overhead we observed was coming from the GPU side, because many of the operations caused by the non-deterministic operations from GPU, if you patch them, then they will basically execute sequentially, order the same. So that's why the training process slows down for certain models dramatically. Just for the randomness itself, as we didn't report the number in the paper, but basically what we see is the overhead is very small. That is that. And the second question is about under what circumstances it is not. So currently our model, the work is mainly done on single machine with single GPU, right? We don't know yet what would happen if this approach was applied into, let's say, like multiple machines, distributed training with a lot of cars. At that same time, like the tool may need to be like tuned to, keep the like, at least what I think is needs to deal with the parallelism of the randomness. Otherwise, probably gonna just mess up the randomness for different cars, and then the whole operation just doesn't work. So yeah, so currently our evaluation and experiments was all done on the single machine and single GPU. So yeah, that's something definitely worth interesting to do in the future.
Okay, very cool. It's interesting. I would have thought that, at least from my work with strace in different contexts, that it would have incurred more overhead, but it seems like in your case, it was very negligible.
Yeah, like strace itself is just run once when you try to functions are introducing the randomness, right? You run it once, right, and the functions in there. And what really run under the hood is the API hook, where you were basically adding another function call behind the real get random call. So that part is kind of, because in general there are not so many calls to the random functions. That's why probably it's not invoking much overhead.
Nice. All right, we have a couple more minutes left. There are quite a few people in this room. If you do have questions, please post them in the chat, and we'll try to answer them in the last couple minutes.
Actually, I have a
Can you hear
question
me?
for you, Jevin.
Oh, sorry, Hongjin.
Oh, you can go first. Yeah, sorry.
Okay. So it's not a question from my side. It's because I also have a paper in ICSE, and I think it's somehow lie between Jeremy's work and Jürgen's work. So Jeremy is about generating the natural variables, and the other work is about how the models makes predictions. So what I'm doing is using those natural substitutions to generate some adversarial examples to attack those models of code. So it's actually because what I found is previously when people are evaluating the robustness of different models, they just randomly select a lot of variables and it doesn't care much about the naturalness issues. So I think maybe it can be an interesting empirical study to do, whether we can find something that is very natural to humans, but also looks not good, which means the models can make mispredictions, things like that. So just take a note here, not a question or something. Yeah.
No, so I definitely know your paper. I read this paper and I thought this is so similar, and I make a note of this in my full presentation. So what's the difference between robustness and counterfactuals?
Yeah.
And mathematically, almost none. that is the honest answer here. And I think we definitely need both in software engineering, but also in natural language processing. We need more investigation between those two things. And there are very few papers that actually picked up on this. So yeah, I'd love to continue this conversation at some point, maybe after this session.
Yeah.
Because I think there's more to get here for sure.
Mm-hmm. Okay.
So I have one more point in my notes that I wanted to bring up. Is that okay? Or does anyone else have a question? All right, then I'll go for it. In that case, Jeremy. So I really, so before you showed how you actually obtain the contrasts, I was like, how are you even getting those? And then I saw how are you, what kind of data set do you need, of manual annotations and translations? And then, these in-batch negatives, I think were a very interesting idea. And so the note that I have here is, if we want to push this work further, right? If you want to improve the similarity, for instance, what pairs of contrasts do we actually need to make this happen?
I'm not sure I completely. So the way the technique works is it only takes positive examples, and it assumes that everything else, every other token that it sees, is a negative example. It doesn't need explicit examples of pairs that are not related.
Oh, then I did misunderstand. Okay.
This is the aha key insight in contrastive learning, and I really wanted to try to get this across, but I only had 5 minutes. It's that every mini batch, you get a sequence of pairs of examples, and you assume that for each pair, those two tokens are very related, and every other token that you see is completely unrelated. It does not matter if they're in the same context. It's just only explicitly positive examples are considered actual positive examples. And you will definitely get tokens that are, actually similar, that are determined to be negative examples. But it turns out it doesn't really matter because they're hugely outweighed by the number of actual negative examples that you get. Yeah.
Nice. Super cool work.
Honestly, it's not mine. It was all cheap. He's a master's student who we could not convince to be a PhD student because he's going to Apple to get paid many more dollars than he would as a PhD student.
Oh, it happens sometimes.
Yep.
We have about a minute left. Last question from the audience, from the speakers. Anything? I think then we're all good. Thank you everyone so much. I think this was a great session. Thank you all for the pitches. Again, look at the full presentations, look at the papers, continue the conversations in coffee breaks on Twitter. It was lovely having you all. Thank you again. Thank you to the audience also for being here. And enjoy the rest of your ICSI. And hope to see some of you at the in-person event too.
Thank you so much, Jordan.
Thank you.